Good evening, all of you. Welcome to the week six series of this chapter, this course, OPAM Practical Applications Design Simulation and Implementation. So we'll wait for just 2 minutes so that somebody wants to join, then they can join. We'll start with this today's live session. So today we'll be talking about whatever we read in this week's six uh, lecture series, and we will be going through constant current drive source, which we will realize using opamps, and then we will see an application of opamp using for temperature sensing, on-off control of temperature, which can be used in industrial applications, which in heating plants and all. So before that, we'll just go through what we studied in previous week, that is week five lecture. So in that week five lecture, we went through non-linear applications of OPAMP, in which we already had covered comparators, window detectors, and Smith triggers. In week five, we talked about unstable multivibrators, how they work, like. As they are unstable because they're both states, like they cannot be in either of the states, they both of the states are unstable. Then we saw their applications, their working, how they work. And then we saw the different waveforms in them, and the charging and discharging time period also we saw. And we realized we derived an expression for the discharging time also and the charging time also. Then we went through monostable multivibrators, in which only one stable state was there, and the other state was quasi state, that is unstable state basically. So in monostable, basically we were like triggering, and then the multivibrator was going into the unstable state. Then after that, it was automatically coming to the high state, that is the stable state. Then we talked about its working and how, and then we realized different waveforms for that. And then also we derived some of these the time discharging and charging time and the total time. But we considered the ideal diode conditions. And then we also talked about how we will generate this trigger pulse. Then we talked about voltage control current source, like how we can use voltage current control current source. So it can be used. We also saw that its applications, like in high current applications and even in low current application. We talked about grounded load, floating load, etc. Then we talked about the assignment questions and some extra questions. So today, in this week six, we'll be first talking about first. So we discussed basically two applications of OPAM. So I will be talking about the first application. So that is the first experiment, we can say experiment one. So the experiment one is to measure the value of an unknown resistor of a cable by constant current drive using op amps. Okay. So we will be discussing about this experiment. So how this was done. So aim was that we have to design and build a constant current drive circuit. So and applications, like there can be many applications to it. So we will be so the aim was to realize this in simulation as well as like in on breadboard circuit also. So aim was to design constant current drive using opamps. Okay. So if we talk about the applications, so why we need this circuit, why we need this constant current drives, why we need constant current. So applications, if we talk about, so if somewhere we have to measure the resistance, like applications if we talk about, so the measuring of a resistance in our we can say when we are looking into many applications, like even in strain gauge also there is a variation of resistance. In thermistor also there is a variation of resistor. So since since like the resistance is changing uh, due to the change in their physical environment, but how we will measure that? So resistance measurement becomes a key point or key, it is having an importance in electronics world. So because of that we can realize many sensors. So like if we talk about force sensing sensor, if we are applying force, then based on the applied force, based on the applied force, the resistance will change. So can we make some relation between the force applied and the resistance change using some signal conditioning circuit? So in that way, resistance measurement becomes important. Force sensing, changing resistance. Okay. Then we have thermistors, as I talked about thermistors. Then also change when resistance will happen. So since the resistance here, it is the function of the temperature also, function of temperature. And we did one example also when we solved one question also, I think in week 4 or week 5 lesson. I think in week 4, when we were talking about Smith triggers, how the Smith triggers can be used to solve this to realize a thermistor, like to measure the resistance of the thermistor. We realized that also in one of the questions. So that was also there. And then there are like micro carbon microphones, in which like here also we can use the we can like see the application of this. So in this, like if we change the acoustical pressure, so resistance is basically function of acoustical pressure. So resistance is based on the acoustics, because the pressure will be varying. So based on the pressure variation, we can measure the resistance. So these are there. So the basic idea behind is that if we know the V and I going flowing through a device, then we can simply do V by I and measure the resistance of the device, or like where the element where this the voltage drop is there and the current is flowing through that. So for that, a circuit will drive a circuit which can do this thing. So we basically will be using a voltage follower here, and we will be attaching two transistors in front of it. So this is the load resistor across which we have to measure the current, and this is where we are giving supply to these transistors. A 10 volt supply is given, and at the input side we have a 1k resistor R1, then we have Zener diode. Okay, then we have voltage of 10 volt here also. So we made the circuit. So in circuit, if you will see, so we have like some components, like we have one op-amp, we have one Zener diode, we have two transistors, we have some batteries, we have some resistors. So, so here at this point, we will achieve some current. So this current is what we are maintaining as a constant value. So this current is having constant value. So this thing we have to achieve, like to maintain a current. So basically for this load resistor RL, this whole circuit will act as a constant current source. So RL will see this I current which is being flown through it, and that current will be constant. So how we will do that? So basically we realize the circuit where if we go step by step from the input side, we have a Zener diode which we were using 2.5 volt bias volt, the reverse bias voltage. So once this 10 volt is applied here, so this will go into reverse bias saturation, and the voltage drop across this will be 2.5 volt. Okay, so 2.5 volt will be across. So here we will get some 7.5 volts of voltage drop. So since this we are having here a buffer, or we can say this is buffer, or we can say a voltage follower. Voltage follower. So whatever the voltage will be at the non-inverting side of the op amp, it will be transferred to the inverting side of the op amp. That is 7.5 volt will be 7.5. Okay. Now we have applied one 10 volt battery here also. So what will it do? So here 10 volt is there. If we have maintained a 7.5 volt across the other terminal of this 1k ohm resistor. So what will happen? The I flowing here will be I, we can say I1, that will be 10 minus 7.5 divided by 1k. It will be how much? 2.5 milliampere. Okay. So this is the current flowing through 1 kilo ohm. Now we have used two transistors here. So since this op amp will drive these two transistors into active mode, and we will be seeing a current flowing through this RF. And since these two transistors are used, so the question will arise why we use two transistors. So this is basically a Darlington pair. The purpose of this Darlington pair is uh, purpose of Darlington pair. So we use these Darlington pairs to increase the gain of these transistors. Okay. So the total gain of the system increases. Total gain of the system increases. So when so we know that this current is the collector, or we can say the emitter current of these two transistors, and here we are getting the collector current of these two transistors. So by increasing the gain, we are basically reducing the we can say the current outside will be approximately equals to the collector current, the emitter current here. This will be approximately equal to the collector current. So basically, we are avoiding the effect of this, like the effect of the base current from here. So that's why we use Q1, Q2 to increase the gain of the system. And then, so now, why this op amp is being used? So op amp is used to develop this constant voltage. So we have across this R3. So to maintain a constant voltage across R3, to maintain R constant voltage across R2. That's how we use OPA. Now this R1 resistor is also being used here. So this resistor is what it is doing. So this if we'll see the data sheet of this Zener diode. Okay. So here we were using LM376 datasheet. So just for the this thing, I will just see what is the datasheet LM376 looks like. Okay, I'll just show you the LM376. So we have this datasheet here. Here. So I'll just open the datasheet for you. So I will this. So here it is. I think this is some another data sheet. Okay, wait. Uh, we will see some general diode. General diode IC. Okay. The iron 431 is there. Let's see what's there in this data sheet of a Zener diode. So we know this is the symbol of the Zener diode, cathode and anode. So if we talk about the the output voltage or this, okay, this is fine. Uh, so in this Zener diode, we can maintain an output voltage of I think 2.5 volts. Yeah, that's right. So we have the output voltage may be set. So it's up to 36 volt. We can set the output voltage for this diode. But I was looking for the voltage. So yeah, input current I was looking at, reference input current. So we can give 10 milliamperes of this, what we say, the input current. So the current which can flow through this generator can be 10 milliamperes. So we will have to limit that current till then. Yeah, it is 10 milliampere. Maximum reference. Okay, that is this is the I reference. This is the current. This is 4 microampere in this case. Okay, anyway, so I was telling like each and every Zener diode is having some current value, current reference value through it, which are the current which can be flown through it. So we cannot exceed that value. So before that, we have used this R1 resistor, which will maintain a 7.5 by 1 kilo, which is 7.5 milliamperes of current through this Zener diode. So that will be here also we will maintain this current to this energy. Okay, so that's why so this whole circuit which so what how so the voltage here we know we know this voltage or and we know this current. So based on that we can get the value of RL. So this is how we have realized a constant current source, and in experiment also you have seen like. In simulation and this like we have made this circuit and we have realized in on the main board also. So instead of RL in experiment, there was a cable, a copper cable was used. You would have seen that in green color, I think. So that was used instead of RL. So yeah. Now we will move towards the next application. We saw this constant current source, right? Now we talk about our next experiment. Experiment two. So here what we are using, we are doing to design and build a temperature controller circuit using opamp as an on-off controller and proportional controller. So we will see here we will be using different types of controller approaches to and that will be built using opamps. So we'll be using that in this case. So first of all, let's see what is this application. So we it's saying that we have to design a temperature controller circuit using opamp as an on-off controller. So uh, so now the type of controller which we'll be using here is on-off controller. Okay. So the aim will be to control and maintain the temperature on the plant as per the user requirement. So this requires So now we'll see the aim of this. First is to control and maintain the temperature, maintain the temperature of the plant. Plant here is some industrial heating plant. We can say heating plant as per the user. Yeah, as per the user requirement. Yeah. Okay. Second aim is uh, so now we need a plant. So we cannot. So we'll have to emulate the conditions in the plants. We will have to find something which can change its temperature when we are using that. So for that we will be using a transistor. Transistor. So this will produce heat, and we will be measuring it. We'll measure. So this is another thing. Okay. Now, another thing in this will be we will have to control the actions also, like based on the temperature. So because so we need control actions, so that we can we can bring the temperature into desired state if it is exceeding from its upper threshold, or if it is going below its lower threshold, then also we want to set the temperature in to make bring the temperature of the pan to its desired state. Okay, that will be also one thing. So the objective here will be another one thing we'll have to keep in mind, that we have to minimize we will have to minimize the error. as much as we can do. Okay, so we don't need much of the error as the system will become unstable in that case. So the basic block diagram we can say, or we can say the basic flow, how the system will be looking like here in this case will be, we'll be having a system of input from this. Then, since we need a controller for this, so we will be using a controller here in this case, and then that controller output will be given to the plant, you can say, which is heating plant. Then we are getting the output, and this output is being feedback to our controller using a signal conditioning circuit. Like the output is being sent to a sensor, and then it is being fed back via signal conditioning circuit. Sensor and signal conditioning. Okay, so it is this is it. So now how we will realize this thing. So we have many a times we have seen this feedback systems and all, but like now we will see, okay, yeah, anyway this is also like it looks simple now. Okay, we have made a controller plant, heating plant, and then we are feeding back this to the again to the controller, and then we are solving. So, but we'll see here like how we can realize each and every box using opamps, and then yeah, if we are using opamps, then we can realize this using. That means we are realizing this using hardware circuitry. So we will see how we can use this, and before that, why these blocks are important, like why the signal conditioning is there, why the summer is there. So that we will also see. So this summary if we see, so whatever the feedback we will get from this output, an error will be there. So this will be generating an error. The V1 input, and here is the V2 the feedback input to this summer. So that will generate an ET. V of t is basically V1 minus V2. That will be the error. That will the error will go into the controller, and based on the error values, and based on the type of the controller, it will be generating some output, and that output will be given to the heating plant, and based on that input given from the controller, this heating plant will change its will control its action accordingly. And again some output will be generated, and again it will be feedback, and this will keep on it will keep on, and it will maintain the stability until unless this E of t, the error, is in certain limit, certain range, certain required range, we can say. Okay, so yeah. So this we'll see the implementation of a error detector. So here we will see. So we'll go. So error detector is basically this block. This is error detector. Okay. So we'll see how this implementation of error detector. Hmm. So for that, we here we can see that we are giving V1 input, and here we are giving like V2. We are subtracting that V2 input from the V1. So how we can realize? So if we recall, we'll see that we have used many summer amplifiers, like in using op amps. Using that summer application itself, we can use that op-amp to realize this error detector circuit, or we have used differential, like op-amps in differential conditions. Op-amp basic idea is itself like it amplifies the differential voltage, whatever is given in its input. So if we can realize a differential amplifier, we can make this error detector easily. So here in this case, we are also doing the same thing. We are using V1 circuit, V1 voltage here, and then we have RN, R1 resistor. So we are basically making a differential amplifier here. Here it is plus, here it is minus. So we are giving a feedback network. And this is 100K. This is V2. Okay. So this is V1. So since this op amp is having a gain of 1, this is having a gain equals to 1. This is a differential amplifier, and this R2 is equals to R1 we have taken. This is R2, this is R4, this is R3 na? Yeah. So this R3 is equals to R1 and R2 equals to R4. So R3 equals to R1 equals to R2 equals to R4. So because of this, we are getting a gain 1 in this case. So that's why we will simply get V1, the output will be equals to V1 minus V2. So we are getting a differential gain here. So this is what this error is about, error, which we basically error V1 minus V2. So using an op amp, we were able to generate the error signal E of t. So in this case, in this experiment, we have seen that we were so in experiment you would have seen like in simulations, like when we were first we were changing V1 and V2 was constant. Then we also started changing V2, and then at particular moment V1 was equals to V2. Okay. So this here also we saw some output was there. Output was there from the output. So this indicated that there is some common mode gain is also there. So based on that, we also realized CMRR, that is common mode rejection ratio, which is given by AD by AC. So AD we know that is 1, and AC we derived using whatever the output we were getting. So we can get AC using V0 we had V1 plus V2 by 2 into AC. So from here we can get AC. So whatever voltage we were getting at that point, from that we can calculate AC. Okay, based on that we calculated the CMRR. So there was we got some 58.8 dB of CMRR. That is okay enough to like it was quite able to. So yeah, so so it was quite able to reduce the effect of the common mode signal in this thing. So that's why we use this. So then when yes we calculated CMRR. Then then after realizing this implementation for error detection, we will see why we need the signal conditioning circuit also. So there is some sensor is sensing something, and then we are using some signal conditioning. So we'll see why we are using that. So implementation of implementation of. So if you have any doubts in between, you can ask or you can write in chat box also. So implementation of sensor signal conditioning circuit, signal conditioning circuit. Okay, so here we'll have to see that which sensor we are using for sensing the temperature. So here we are using LM35. LM35 sensor we are using sensor to sense the temperature. Now this LM35 is having its own, we can say some requirements or we can say limitations also. Based on that, we will have to set our circuitry accordingly. So when we will look into this LM35, we have it is given that sensitivity of this is equals to 0.1 volt per degree Celsius. Okay, sorry, wait. It is 10 millivolt per degree Celsius. But the sensitivity which we need for our input is required sensitivity is required sensitivity is zero point 0.1 volt per degree Celsius. So we have to bridge this gap. So we can see the datasheet also of LM35. So here it is given, see the scale factor. So for each 1 degree Celsius change, we are having 10 millivolts of change at the output. Okay. So based on this requirement, we will be requiring a signal conditioning circuit. So how we can use that? So we will be having a sensor. We can denote this as sensor output. We are giving the sensor output, whatever we got at this terminal. Then we will make one. We will realize one inverting amplifier. And in order to reduce the effect of bias current, we are using these two resistors, R3 and R4. This is 10K. This is 100K, and we are using this as 10K and 100K. So the parallel combination of this will remove the bias effect from this op amp. Okay, so then we are using another amplifier, another inverting amplifier, that is the output V naught, that is being fed back to the this V2, that is basically V2, which we are now seeing. This is basically V2. This is the signal which is being fed back to the controller. Okay, so here also we will reduce the effect of bias using the okay, in this case it will not be, let's say this is R5, this is R6, because we are using 100K, it is 100K here. So it will be the parallel combination of 100K and 100K. Okay, so what will happen when we are giving a sensor input, like sensor, basically this is sensor output, when we are giving an input signal from here. So this op amp will amplify that signal to 10 times because it's having a gain of 10. But it will also, so if we give a signal like this, so it will make it like this. But also it will increase the amplitude, but at the same time it will introduce a 180-degree phase shift in this signal. Then again we will be using one another op amp, another we can say negative amplifier, so that what it will do, it will make the signal again come back to 0 degree phase. So we got this. Okay, so we can realize this using a non-inverting amplifier also. So yeah, if we can give plus minus, we can give signal our sensor output. You can see sensor output from this side. This is R1, this is R2. We will get a gain of 1 plus R2 by R1, which should be 10. V output equals to Vi into, this should be equal to 10, or I can write it separately. So here 1 plus R2 by R1 equals to 10. So R2 by R1 will be what? Will be 9. So R2 should be 9 times of R1. So if we are using R2 as uh, let's say R1 is 10K, then this will be 90K. So using one amplifier also we can realize this. So now by using the signal conditioning circuit, we are able to achieve a gain of 10. Based on that, we were able to achieve the sensitivity of zero point 0.1 volt per degree Celsius. So for each zero point 0.1 volt change, we'll be having 1 degree Celsius change. For each 1 degree Celsius change in the sensor, we'll be having a zero point 0.1 volt change at the at the output of the signal conditioning circuit. So that is there. Okay. So now this was the another circuit. Now we will see the implementation of the heating circuit of plant. Uh, Now we have achieved what we have achieved. We have seen the signal conditioning circuit of this thing, this block, and we have seen the error generated, this error detector circuit, signal conditioning circuit. Now we are looking into the plant heating signal conditioning circuit. Not signal conditioning, but the circuit realized using opamps. So implementation of heating circuit, heating plant, heating plant, yeah, circuit. So as we decided that we will be using a transistor in this case. So for that, how will we do that? So it is simple. We'll be using a source, voltage source, and a buffer, or we can say voltage follower. At the output of the op amp, we will be connecting a resistor. Then we will be giving it to a transistor. So this transistor will be acting as a change in. So this resistor is 0.1 volt, 100 watt. This transistor we are giving a supply of 15 volts. Okay, this is there, and this is 180 ohms. So this is the circuit. So based on the change in this, as we will apply more supply, so we will be changing, we will be increasing the supply. This we can say V supply. We will be changing in 0.5 volt steps. So we'll be increasing the voltage. So as we'll be increasing the voltage, the current through this R1 will increase. So this current through that this transistor will also increase. That will heat the transistor. So in this way, we will be using this transistor as a plant circuit. Okay, so this is basically a voltage to current converter. Voltage to current converter. As in this case, we are basically applying a voltage and it is being converted into the current, which is flowing through this R1 resistor. Right. So this resistance we have maintained constant, and yeah, so there's a current flowing through this transistor is being dependent on. So yeah, so the current flowing through this transistor is dependent on the voltage which we are supplying here, and we'll be increasing this voltage so that will be the voltage of the current flowing in this transistor, it will increase, and thus it will heat the transistor. Okay, so next we have realized error detector, sensors, and signal conditioning circuit for plant heating, and then now we'll look into controllers. Implementation of on and off controller. So when we talk about on and off controller, so in this case we used one Smith trigger, a signal circuit which is working similarly like Smith trigger. So what we did, we had an op amp like this, which was being given input into its positive in non-inverting terminal, and the feedback was also given from the non-inverting terminal, that is this 100k. So we had our error input from this side, that is E of t was from this side, and then Uh, this was R1, this was R2, basically a voltage divider circuit, and we were giving some supply here, V plus we can say, and some I1 current is flowing here, I2 is flowing here, and then some I3 is flowing here in this case. Okay, we are having output. So output will be either positive or negative saturation, since this is in positive feedback circuit. And this output, we'll see this is input to the heating plant. Heating plant. So as we can see in this block diagram also. Yeah. Okay. Yeah. Or yeah, but yeah, since we cannot, yeah, we can use also one signal conditioning circuit also after this, as we are getting some voltages like this. So if we have to make that linear, these voltages we want to make it linear, so we can use this in us. We can give it to a signal conditioning circuit, then to a heating plant. We can do this also if we don't have to directly give it to the heating plant. So yeah, then it will be something, maybe we can accept some linearization, that is this, and then we can drive our heating plant accordingly. So now if we'll talk about the equation for this, so if you use KCL at node A, so then it will be uh, V plus minus V1 by R2 equals to V1 by R1 plus V1 minus V0 1 by R3. So if you have any doubts in between, you can ask or you can write in comment sections also. Okay. So yeah. So this is KCL at node A. So if we'll solve this, so we will get V1 equals to R equivalent divided by R3 into V naught 1 plus R equivalent by R1 V plus. So R equivalent is basically the equivalent circuit, or the equivalent the resistance of this R1 and R2. Okay. Hmm. So this was the V1 voltage here, which we saw. So now we got the output as R equivalent by this thing. So now in this now so if we'll go back to the lessons of Smith Trigger. So what we studied there. So its Smith trigger is having some upper threshold, V upper threshold, and it is having some lower threshold. Okay. So what happens when a signal comes? If it is above the VIT, this if it goes above the lower threshold value, then the signal will become,
Excuse me, sir.
yeah, yeah. Tell me.
Sir, here what is R equivalent, sir? Is it parallel combination of R1, R2, R3?
R1, R2, R3. Okay, wait. I think it's the so if we'll see at the KCL, or no, or we can say if we'll just solve this thing. Okay. So okay, I will solve this to you. Solve this for you. So what will happen? V plus that will be 1 by R2 minus this is V1. Wait. So V plus this is V1. Okay. V plus by R2. If we go V1, this is 1 by R2 plus 1 by R1. Then we have okay, minus V1 by R3 also. Then plus this is minus V0 1 by R3. Okay. So this will be V plus by R2 plus V0 1 by R3. Then we have V1 1 by R2 plus 1 by R1 plus 1 by R3. Okay. Now, yeah, so this is the R equivalent. Got it?
Yes,
So
sir.
if we compare from this equation, then R equivalent, yeah, it can go. So it is the parallel combination of R1, R2 and R3. Yeah. So now,
Okay.
okay, got it? Yeah.
Yes, sir.
So now, yeah, I was telling you that since we know the this application of Smith trigger. So once the signal goes above the lower threshold, so what happens? Uh, it initially, let's say it was at height stage. So since it goes above the lower threshold, or we can say, let's say initially it was at lower voltage. Here we can say lower voltage. Then once it goes above the lower threshold, then it will be in high stage. High state. Okay, so it will remain in high stage until and unless it again reaches the lower threshold. Or yeah, I think. So once it reaches the upper threshold, then it will be at higher stage. Before that, it was at lower stage. So once again, if crosses the lower threshold, then only it will be transitioning into the lower stage, that from high to low. But if it is in between this, like it is like varying in between this, or it is varying at the upper threshold, so what will happen if it is there? So initially if the signal was low, so if it is varying here, then it will remain low. But once it reaches here at the upper threshold, it will go high, and since here variations are also there, it will not affect the output of the Smith trigger, it will remain high. Okay, this what we studied. So here also we are using the same principle. So so if we see here, we have decided a lower threshold limit, that is the lower temperature limit of the plant, and we have decided the upper threshold, that is the upper limit of the plant. So only when there is a transition. So if the temperature is being is changing here, then nothing will happen. Once the transition goes like this, the input signal goes above this value or it goes below this value, then only our Smith trigger, or we can say the on-off controller, will give input to the heating plant circuit, and then some changes we can observe there. So yeah, so this is the basic Smith trigger principle which we saw by using the two reference voltages, one this and another this. So in experiment also we'll see. I think we'll see in the week 7 lectures how we'll be using this. So now we'll come to the signal conditioning. Signal conditioning of on-off circuit, of on-off controller. So, first of all, why we need, because we are getting a output like this from this on-off controller. So we need something, some sinusoidal output or something. Okay. So it is since the output is only, uh, you can say the output is only V plus and V minus. So we need some linear in, so some output in some sinusoidal waveform, something like that. So for that, what we can do, if we can make simple inverting amplifier. Again, this two resistors are used to compensate for bias current IB compensation. We have this is the input from the on-off controller, input from on/off controller. Uh, then we are having some output. So this is R5, this is R6. Hmm. So this we will take as 100k. This is as 1k. So here, like we were having a plus minus, let's say plus 15 volt if it was the supply, then minus 15 volt. So it was varying like this. So if we will give, so this the gain of this amplifier is basically 1k by 10k, 100k, that is 0.01. Okay. So so when we are, so this is V naught. Let's say this is V naught 1. So V naught by V naught 1 is what? 1k by 100k, and this is equals to we are giving yeah, the voltage we need as, this is as 1 volt, and the input is 15 volts. So it is like this. Okay. Okay, this V naught was 1 volt now. Yeah. So V naught is 1 volt. So V naught 1 or we can say it like this. Hmm. Hmm. So V naught is equals to V naught 1 into gain. So, gain which we are having is in this case is 1 by 100. So V naught 1 whatever the input we are giving, so it is this. Okay. So based on the input value, so we are basically reducing. Uh, we are setting the output to a like some set range, so that we can accordingly give this to the heat. We can give this to the plant heating circuit. So using this gain amplifier, we are basically reducing the gain, and then we are giving it to the plant heating circuit. So since this input was at high voltage at V plus and V minus, so we have reduced that gain, we have reduced that amplitude values, and then we are giving it to the output voltage and input to the plant heating circuit. So this is the signal conditioning for on and off controller. Okay. Yeah. Now, so since this was this we read here is we studied about on and off controller. So there is similarly we have a proportional controller also. Proportional controller. So in this proportional controller, the output of the controller is directly proportional to the error signal which is being fed into the controller. So this we saw. This is basically V2 minus V1. So this we saw in the block diagram. So earlier we saw that. So it is proportional to this, and the proportionality constant is given by Kp E of t. Okay. So now this is the proportionality constant. So we saw one example of this water control well in which we were having a tap like system, and we were having a well valve in that, and it was being supported by a fulcrum. It was looking like this A and B, and it was then there was one we can say a bob or ball which so water was flowing here, and since the water will increase, this bob uh, will come. This ball will come up, and this fulcrum will be like this. Okay, so this A and B, so this ratio will be there. So this is the x. We can say the position of this wall. This is the wall. So as this will increase, it will it will come down, and slowly after some point, once this is completely filled, this will close this wall. This will close this tab basically. So we saw here that the output, this is the output y, is being given by a by bx, where this is the constant, and x is the position of the wall inside the tab. So this was an example of proportional controller. So, but how we will realize this using an op-amp circuit implementation of P controller. Okay, so basically we can realize this using two op-amps. We have one A1 op-amp, we can say, that is again we have given feedback compensation to the bias current. This is 100k. This is 100k. Okay, this is the error signal which are being fed into this op-amp. So we have uh, another op-amp, that is A2 we can say, that is having 100k here, sorry 10k, and this is V0. again we have a bias current compensation in this case. So what is happening? So this is basically inverting the signal here in this case. So we have given some signal, some error signal like this, and this signal, this we have considered this 10k to be a variable gain register, where like we are changing its gain so that we can choose our gain according to our wish. Gain we can we can we can set the gain of this of A2 amplifier of A2. Okay. So and this will again make the signal uh, come back to the 0 degree phase shift. So these in these two way we can simply make a proportional controller. So based on if we are increasing the error, so accordingly our output this V naught will be changed, and this is let's say V naught. So if V naught one is what error into minus, let's say this is R2 R1, so minus R2 by R1, okay, and we got V naught one. So V naught will be what? V naught will be we can say this is R3 or R4, this is R3. So this will be again minus R4 by R3 into error minus R2 by R1. So we will have this minus minus will be plus R4 R3 into R2 by R1 into error. So in this case, this is our KP and this is our input signal, or we can say the error signal. So this is acting as a proportional controller. Uh, Proportional controller. Okay. Yeah, this is KP. Huh. So now we also talked about the PI controller, proportional PI controller, PI controller. So in PI controller, the output of the op-amp is directly proportional to ET, that is the proportional controller which we saw, and in integral controller, it is basically directly proportional to the integration of the current, the integration of
Sir,
the error. Yeah.
sir, in the proportional controller, how do we decide the gain, sir? We are multiplying error signal with gain, no? So how I can decide that gain?
So gain is this basically the combination of R4 by R3 into R2 by R1. This you can see here.
Ah,
Uh,
sir, that is that I understood, sir. But how do I come to know a number with which I need to multiply my error signal?
oh, that is
Ah,
okay. Okay. So I think we are giving this signal. Okay, we'll see. We are giving this signal to the plant circuit. Okay, and plant circuit is having. So basically, this controller signal is being given to implementation of yeah, that is the plant circuit. Implementation is this. Hmm. So yeah, it will depend on like what at what stage our on off was there, but based on that we will get some feedback. So we'll get some feedback that was that will be the error phase. So hmm, this we know that we are giving the signal to our plant circuit. Okay, plant circuit heating plant circuit. Now I'm not able to come to a particular how we can say, yeah, it will depend on the like the requirement, if it is, let's say, okay, let's say, we'll see one scenario where where the output was, let's say, what, the set value was at 100 degrees Celsius. Okay, so beyond that, it will get off. So our signal, let's say it is 75 degree Celsius something. So it gave the so error signal will be 25 degrees Celsius. That is like zero point 0.1 millivolt, zero point 0.1 volt based on this. So it will be 2.5 volts. So we are giving 2.5 volts. So I think Mm, yeah, like in lectures also, like it will depend on the plant requirement. So whatever the plant requirements will be. So if see if our signal the signal normally if the signal is in, let's say, microvolt range or millivolt range. If the scale sensitivity or the sensor LM35 which we are using, it is not that good. So we will have to then increase the gain here accordingly in the A2 side. But if the error is like, let's say, we are having the error is in, like, let's say, millivolt range, or we will say volt range, not millivolt, let's say volt range. So we don't have to amplify itself. So then we can like set the gain itself to 1, or we can reduce the gain also. So it will depend on how much the error signal that the heating plant can generate. So let's say like our heating plant is deviating. Let's say, so we have a threshold. Let's say for a heating plant we have a threshold of 25 degrees Celsius and 100 degrees Celsius. So between that, if there is the things are there, then it is fine. Okay, if the signal is varying, and the output from the signals using LM35 we are having in let's say in millivolt range. Okay, so that millivolt range is being fed back to this controller. So now, if our circuit are we can measure this millivolt range easily, so then it is fine. But if it is very less value, then we'll have to increase the gain. So it will all depend on this heating plant requirements. So I don't know whether I am able to like clear your doubt or not. But yeah, doubt. Yeah, your question is nice. Yeah, question is nice.
So are we able to design a variable gain possibility, sir?
That we can do variable. Yeah, instead of like manually doing this, changing this this register, we can variably also we can uh, do that. But then I think again we'll have to give some feedback to that variable gain, uh, because yeah, if let's say we instead of this we have some variable gain uh, a register controller. You are saying this now, Anil?
Sir?
You are saying this now, like we will have to go for a variable gain this.
Ah, yes, sir. If
Huh.
you say that we want to change the gain, so then is it mandatory that we need to go for variable gain?
That is if we have to change the gain, then we'll have to go for the like variable gain thing. Mm.
Okay, sir.
Okay, but again another question is that if you have to change it manually, then okay, it is not a big deal. But if you have to change it again with some feedback, then there is like then we'll have to think. So then we cannot do manually. So if it is want to make automatic, so we'll have to like give some feedback to this variable gain circuit, and then we'll have to see how it works. Okay. But
Okay, sir.
for timing, you just think that okay, we need some variable gain, and it can be adjusted according to the requirements of the heating plant. Fine.
Okay.
Yeah. So then we went for PI controller. So in PI controller, we looked at it is having two components. I think we'll see more in this future classes also about this. So just for the brief introduction, this is like U of t is equals to basically Kp of E of t plus Kc integration E of t by dt, and simply if we write in the S domain or the frequency domain, so this is k, we can say ki by s. Okay, this is u of s by e of s. So these two are the equations for the integral gain. So yeah, that was there. So we saw that integral gain, when it is small, the controller will be like slow, and if it is large, then the controller will oscillate and become like unstable also. It will become. So there is like a integral gain. Then we also saw that how we can realize this integral gain. Uh, so if let's say some proportional controller, I we can use here. So this is similar to the proportional controller gain we are getting. This is 100k 100k, and we are giving error input. This is, let's say, 1 megaohm, and this is capacitor, which is around 1 nanofarad, and this is the error input. Okay, and again we can have that bias compensation here. Now this is being these both are being uh, we can say added, and then given again to another op amp, which is having 100k here and 100k here. Again that bias compensation, and then we will have this. Okay, this is 100k, this is 10k. If you have to reduce the bit, so each and every op amp is having some, like let's say this is a1, this is a2, this is a3, this is a4. So we see, so this a1 is here, it is doing like it is setting the gain, the gain.
Sir,
Yeah.
sir, in the last op amp, why we have not taken care of bias compensation, sir?
Or you can take it. You can take it if you want to.
Okay,
Yeah, yeah, you can
okay,
take
sir. Okay.
it. No issues. I will make it. Yeah. Okay. Yeah. So now this A1 gain is setting the gain for P controller. Then we have A2. That is to set integral gain. So as we know, this circuit is an integral circuit which is used by which is realized using an op amp. So this will integrate, and this will like the upper one will like simply give a proportional gain. Okay, then it is being fed to A3. So A3 is basically adding these two signals. So A3 we can say, or we can say A3 is summing the two inputs, from one from this and another from this, summing the inputs to it. And then this is an attenuator which we are simply using. Based on the requirement, we can set the gain here. Okay. So again, to meet the requirements of the plant, we can use the attenuator here accordingly. Now, one more thing. Yeah, after that, like in the last lecture, it was being told that we use error, where it is the error detector is there. So in this error detector, we use a differential amplifier, but instead of that, we can use an INA also. INA, instrumentation amplifier. Then we saw how this INA can be built using three op amps. Okay, that is okay. That is also fine. Something like this, yeah. Yeah, something was, yeah, some things, yeah. Three op amps are basically used in that. So the case, but the problem is that the INA is a little costly. Okay, the INA is little costly, but the positive, the positive the advantage of INA. What is the advantage of INA? That it provides high CMRR. If the budget is there, then we can go for INA, because it is having high CMRR, that the common mode rejection ratio is good. And the another important thing is that it can avoid loading effect. Can avoid loading, because I will draw it here in the last. Yeah, here. So basically, the input to the INA is given using this V1 and V2. We know we will not. Then there is a rest circuitry, but we are interested in this input of the op-amp. So here what is happening, V1 we are giving to the non-inverting terminal, V2 as similar to the non-inverting terminal of the second op-amp. So here, since the input impedance from this side, we can see that it is like very high. So the loading, we cannot, the loading will be almost zero here, no loading here, INA. But in differential, what we looked into differential when we were using error detector using differential gain amplifier. So we were giving V1 here, and we were giving like V2 from here. Okay, so there was some feedback like this, and so here the since the current is there, so current, okay, it is here, so current will be going like somewhere here or something like that. So here the loading issue will be there, not loading only. But since we were using this as a gain equals to 1 amplifier, so there is a problem of register mismatch. So this we were able to realize when R4, R3, R2 and R1, let's say these all were equal, R3 equals to R4 equals to R2 equals to R1. So if some error mismatch happens, because we know the resistances which we take that are not absolutely of the same value as we think of, because there are some tolerances in these resistances, so they cannot be of this value. So what will happen, based on this there will be some change in the gain. Let's say if this is having percentage X of tolerance, or it changes like percentage X, so this will not be equal, so this will not be like this, so gain we cannot achieve as one. So it will also affect the CMRR of this differential amplifier, this thing, CMRR, because our differential gain will change, will vary, I think it will reduce. So based on that, CMRR will also reduce, because CMRR is AD by AC. So that's why if there is some mismatch, it will affect our CMRR. So that's why also we should avoid differential gain amplifier. But if we have to reduce the cost, then we can use this differential amplifier. Otherwise, we can go for INA. Okay. So now, yeah, this was there. I think, yeah, this much. Huh. Tell me.
Sir, it is taught in the lectures that instrumentation amplifier is having certain minimum gain, and that
That
is
is
why we
also
are
there.
not using here.
That is also there, that it is having gain of, let's say, 5 also. But yeah, but not, I think all the INAs are having minimum gain of 5. But still, yeah, that is there. That gain is they have mentioned as 5. That is for good, yeah, good ANAs. Uh, but normally we can set the gain as 1 also. That is there.
Okay, sir.
Yeah. So I think you can look into 8620. 8620, I think that is one of an INA from Analog Discovery. So it is having if you'll not use that RG register we use the video. Okay, what happened? Hello? Yeah. Yeah, yeah.
Sir,
So you can use 8620 INA. You can check the datasheet of 8620. I think when you will be using RG as infinity, I think then the gain is 1, I think. Something like that.
R, sir, how much, sir? RGS infinity.
Infinity means, see, there is an IC. There are ICs, so there are like, let's say two pins are there. So what they tell, like you will have to attach one RG register here, so as to set the gain of that. Okay, I will just open the internet and I will show you. Wait, 8060, 8060, AD, AD 620. Hmm. Hmm. So when we set the gain, we'll see if this is having one gain or not. Uh, yeah, yeah. See the gain equation. See, this is the gain equation of this 8620. You can see now 49.4 kilo
Ye-
ohm.
Yes, sir. Yes, sir.
So what happens if you will make this RG as infinity? So this whole will become 0. So then gain will be 1.
Okay. Infinity means we need to take large value.
Now I will show how you can make RG as infinity. Uh, when you will see the pin diagram of this pin diagram. So RG we have to connect between this. So this is the RG value. Between one pin and the eighth pin we have to connect the resistor. So this is the value of RG. So if you are not connecting any value, so if nothing is there, then what is the RG? Tell me.
Infinity.
Yeah. So you don't have to attach any resistor there. So it will give a gain of 1. Okay. So that is the
Okay,
case.
sir.
So now we'll come back to this. Yeah. So we discussed the things about what we read in this week 6 lecture. Now we'll come to the this assignment questions. So now simply just I will give you hints and basic ideas how you can solve, as I cannot tell you the answers. Uh, yeah. So yeah, all this assignment was easy only. So yeah, the first question was a proportional band setting of 175% is equivalent to a gain setting of. So we this is a simple formula. This proportional band is equal to 1 upon gain. So I think I gave the answer itself. But okay, this is the formula you can use here. So you can get the answer from here. Okay. Now coming to the next question. The procedures that must be taken in the correct order to increase the system stability. So there are different procedures. So we'll see. So we are using a negative feedback, then we are reducing the gain, then we are giving it to a we are basically derivation. We are doing the derivative of it, taking the derivative of it. Another is reducing the gain first, then using the derivation fraction, and then giving it to the negative feedback. That is also one possibility. Then another is reduce gain, then use negative feedback and insert derivation action. Then there is like first insert derivation action, then use negative feedback and then reduce the gain. So one thing we should keep in mind that whatever action we have to do, okay, we can do if we can do the action can be more done in a controlled manner if the signal which we are inputting to that action is in a controlled manner. So if we are giving a controlled signal or the signal which we know cannot go beyond limits, so then we then if we are performing some actions on that, then it is preferable. So that's why one thing we can think, any action we can, if we want to do, then we can do after in the end, once we have signaled the condition, we have like conditioned the signal. Once we have conditioned the signal, then we are providing some, then we are doing some action, then okay, it is fine. So that's why one thing is that we can do this action in the end. Then the other things are like whether you can use a negative feedback or reduce offers, you can reduce gain. So you also know that when we use a feedback, we can like we can control the gain. So you can yourself decide which thing can come first and which bit can come second. Okay. So this you can do. Second question. Now the third question is the input to the controller to a controller is desired variable signal, send signal, error signal. This is also very simple signal of its amplitude or not dependent. So you should think okay, what controller's job is. So based on that you can answer this question also. Okay. So then yeah, the transfer function of PI controller is it is also very simple, straightforward question. So another name for PID controller is, so you can like see okay, what is the another name of the PID controller, like in any textbook you can go through it and you can check it. That is also easy. Now the next question is the op-amp circuit, or wait, yeah. Hmm. Yeah. Okay. So the open circuit shown below, the load current will be. So we have to find this load current. So whenever you see this such question, so then you can simply go with KCL and KVL equations at the inverting and non-inverting terminals. So here, if we see, let's say this is what we'll say, this is V1. Okay, yeah, this is V1, and this is by virtual short. This will be equals to V1. So what we can do, we can solve one KCL equation here, one KCL equation here. So it will be, if we solve at the above with the negative feedback, then it will be V1 minus Vs by R1 plus V1 minus, let's say this is V output, V1 minus V output by R1, okay, equals to 0. Another equation will be V1 by R2 plus V1 by Rn plus V1 minus V0 by R2 equals to 0. So this is IL. Okay. So IL equals to my you can say minus V1 by R2 minus V1 minus V0 by R2. So based on this, if you will substitute V1 from this equation into this, so you can get the answer for this question. So this is also okay, easy. So the next question is, as shown in the figure below, the output voltage of a circuit will be, assume op amp is ideal. So yeah, so they have assumed that op amp is ideal. So we have to think how we have to solve like what is the output of this thing. Uh, is V not. So in this case, simply see what can happen. So this is a one circuit, another is this circuit. So if we don't have any let's say any idea about how they function, then it may be a little difficult. But anyway, it is still easy. How we'll see. So we can see what is the what we can think of how okay what is the current flowing in this thing. Okay, so let's say this is Vs. This is Vs. So the current that is I that is being flown from that is started from this Vs voltage, this Vs source voltage, and then through this 10 ohm it is passing through 10 millihenry, then it is passing through 100 ohms, then 10 microfarad. So what we can do? So simply V2 the current that I equals to V2 by 10 that we know. Okay, so current expression we can get easily because this is 0 volts, this is ground, that virtual short can happen here, and the current expression is sorry Vs, this is Vs by 10. Fine. Now we know one thing that this inductor, so we can say this is V01. So V01 will be what? It will be minus of, we know this expression and di by dt. Okay, this is the voltage drop across the inductor. So now we know what is I. I is this thing, this expression. So we can get we can get this expression from there by differentiating that expression. So yeah, we will have to differentiate this thing. Yes. Okay, one thing. Another thing. Now we are giving this again. Again, now we separately think of the circuit. Then what will happen? The current, this current. What will it be? It will be V naught one by 100. That is the current here. And this current is being fed to the capacitor. Again, what will be V naught now? It will be minus 1 by C I dt. So now in this case, we will have to integrate this thing. So this is acting as a differentiator. This is acting as a integrator, as an integrator. Now imagine the question which we just faced here. This question, the procedure that we stay correct order in the system solidity. So now see this derivation action. Now we saw that it is being used like performed using an inductor. Okay. So now if we will not be giving a control signal to this thing, that is like this voltage, this thing. If this will not be controlled, then This circuit will be creating issues. So that's why first control this circuit, then create it, release some action, then give it to perform some actions. Okay, that's what that question is saying. So you can see that one thing here also. So based on these, yeah, the derivation and the integration action, you can solve this thing. Fine. Now the eighth question. In a proportional temperature controller, if the quantity under the heater increases, the offset will be. So this again you can answer as we know in proportional this controller. Hello, yeah, okay. Yeah, in the proportional controller, so we have like there's some always a set offset. So the signal will be like this. It will not be. This was the set point. This is the steady state value. Steady state value. So this is the offset. There is always an offset there. So you can answer like control the like the quantity under the heater increases. That is basically we can say the load of the heater increases, then the offset will be. So this is also okay. So when the another question, when derivation action is included in the proportional controller, the proportional band. So whenever you will see like in proportional controller, that will be like PD controller. So P behaves separately, D behaves separately. Okay, yeah, the final outcome is based on their like their combined output. But here we are talking about only the proportional band. So this proportional band is it depends on only we can say as we saw earlier also it is inversely proportional to the gain or we can say KP. That's all. So then based on that you can answer this also. Now last question, how natural frequency and damping factor in the conversation changes when we use a derivative controller? So, they are meaning the like in P controller, we are using when only P, the omega n is given by KKP, that is the T is the time constant, K is the gain of the system, KP is the proportional gain. Okay, gain K is the gain of the plant basically. So this is the natural frequency, and zeta, that is the damping factor, is given by 1 by 2 K KPP. Fine, but when we use P plus D, the derivative controller, then the natural frequency is it's same. Okay, it is KKP by T only, and zeta is 1 plus KKP 2 under root K KP into T. Okay, so this is so based on this you can answer this question also. So yeah, so assignment questions are done. If you have any other doubts regarding lectures, then you can ask me. Yeah.
Sir, in fact, I have question in assignment 4. Can I ask, sir?
Four, yeah, okay, four. Okay, tell me. You will have to tell me the question. I don't
Question
know.
number 8, sir. Question number 8. Assignment 4, question number 8.
Okay, wait. Assignment. That was in. Yeah, I got it. Question eight. That was what about what? Can you wait, question eight? Yeah, I got it. I think. So there was some. Okay, that we had to give the output of that Smith figure.
Yes, sir. In fact, when I simulated it, I got the output as minus 3. And when I used the superposition principle, assuming one input is available at one time, I
Huh.
got the output as minus 3. But the answer is being given as plus 20.
No, did
Assuming
you?
that positive feedback plus or minus we set.
So did you apply the positive feedback in that in simulation?
Yeah, I have connected as it is in the question or whatever the way circuit is given.
Mm-hmm.
I got the output as minus 3, and even manually I calculated applying superposition principle. I got the output as minus 3 under the assumption that the gain is very large, open loop gain is very large.
Can you share your do you have that simulation?
Yes, sir, but right now I
Okay.
am using mobile phone. Right now I am using mobile phone, or
Okay.
else I can share, sir. Maybe when once I use my laptop, I can share it.
Okay. But it should not be. See, I will write the question for you. So it was like this, no?
Yes, sir.
Resistor was there. This is plus minus. So this was grounded. It is like this. Uh, so this here we were giving 3 volts.
Ah,
So
yes,
this
sir.
was output, no? This question. So we had to decide, okay, what is the output? This was plus 20 volt minus 20 volts. 20 volts. So yeah, so how you so what you were telling about superposition? Tell me again.
Sir, first I assumed that
Hmm. That only this is
hmm,
there. This is zero.
yeah, V plus is there, no, sir. V plus here, V plus is not equal to V minus.
Yeah, that is fine.
That V plus I can find it as one time due to the plus 3 volts and one time due to the output voltage.
Okay. You are saying. Okay, so you are saying you grounded output when you were finding V plus using 3 volts.
When I found like that, I got minus 3, sir.
What V plus, na?
Ah,
See, V plus will be anyway. It will be like whatever, like 20. See, V plus will be 20 into the beta factor. That is 1 by 2 now. So it will be 5, I think. That is beta into V saturation we say na V plus. That should be, yeah, R and R are equal now. So beta is, sorry, 1 by 2. 1 by 2 na, 20 by 2, sorry. 20 by 2, sorry. Not 5, it is 10 volt. It will be 10 volt. This will be, I don't know how you solve. You cannot solve superposition here, na? You cannot use superposition. Ask me why.
sir,
Why? Huh.
I cannot apply superposition, sir.
No. Why? Because superposition has a limitation that it can only be applied in linear circuits. But when we have given a positive feedback, then it is a non-linear circuit. It is behaving like a non-linear input. Got it? So it is
Okay.
not at all a. See, we have the output of the op-amp characteristics are like this. This is normally for any op-amp. So in this region, if the op-amp is working, that we say that is a linear region, and this is normally happens in a negative feedback. But when it comes to this region, then it is a like non-linear. Got it? So you cannot solve.
Sir, 1 second, sir. I'll verify this once.
Yeah, you just
1
check.
second, sir. I'll verify, sir. One.
Yeah, you just check again. I think you have done some mistake in simulation here because superposition anyway we cannot use here. Talking about this simulation, there's some mistake in that. I definitely think you have like connected this thing non-inverting terminal, like you have like given input. You have given a negative feedback, I think.
It is there in my account only, sir. I'll try to open that simulation.
Yeah, okay.
Sir, can I share my screen, sir?
Yeah, yeah, sure. Yeah, you can.
Sir, is it visible?
Yeah, yeah. Can you zoom? Okay. This is fine. 0 volts. Oh. Hmm. 0 volts. Hmm. Oh, this is possible. Uh, online. Can you invert this terminal of the op-amp again?
Which one, sir?
Oh, you cannot. Can you do it? Invert the op-amp terminals, like plus to my negative again, if possible.
Uh, yeah, I'll try, sir. Yeah, because it is a mobile. As it
Yeah,
is
yeah, that's
already
what.
being done, I am able to simulate this.
Uh,
So you want me to invert the terminals of plus minus. That's all,
yeah,
sir.
yeah, that's all. I just want to see, is there any glitch in the like software, or that it should be?
Yeah, in fact, actually, initially I thought that the answer is plus 20 only.
Uh,
But once I simulated, I got the answer as minus 3. I was a doubt that whether simulator is right or I
uh,
am wrong.
uh.
I believed much with respect to simulator, and I tried once again manually how I can get this minus 3. So then when once I applied superposition principle with op amp gain as assuming very large, I got minus 3.
But yeah, you cannot use superposition. But we can do one more thing, that maybe next class I can clear this doubt. I will use another software like LT Spice or Tina TI. Have you heard of that?
Ah, yes, sir. LT space I have heard.
So I think we will realize this circuit in that, and then we will check. Then we'll check.
Okay, sir. Okay.
Hmm. Maybe if that is the case, then yeah, we can. Okay, we'll see. We'll see. Next class I will clear this thing. Okay. I will just write this
Okay,
in
sir.
this.
Okay, sir.
Okay. So any other doubts?
No, sir.
Okay. So I think yeah, that's all for today. So we'll meet next week, this time only, 6 o'clock. Okay.
Okay, sir.
Yeah, yeah.
Okay, sir.
Thank you. Thank you.
Thank you. Thank you, sir.